Okay, welcome back everyone. We're going to be starting in about 2 minutes or so, but Néstor, could you please share your screen just so we can check that everything's working?
Yes, 1 second.
We may have just lost Néstor, which is why we do these tests in advance. Hopefully I'll be able to get back in.
Don't panic, I'm back.
Welcome back, welcome back.
See. Go, and then you should be seeing my screen now.
We can indeed.
Okay, awesome.
So, I'll give everyone their promised extra 20 seconds before introducing you.
All right.
Okay, so welcome back, everyone. We have just lost. There we go. Okay, so we're now going to be hearing from Néstor Espinoza from the Space Telescope Science Institute, telling us about how to constrain the mornings and evenings of distant worlds and all of the state-of-the-art and future prospects. This will be a 40-minute invited talk. I'll give you about a 5-minute warning towards the end, Néstor. But without further ado, please take it away.
All right. Thank you very much. I'm really excited to be giving this talk here. I'm excited by everything that's happening. I've been following the talks, and they have been absolutely spectacular. So I hope this is up to the bar of all the talks that have been given. So basically, the idea of constraining mornings and evening and distant worlds, it's a huge concept. And because it's such a huge concept, I want to start from the very, very beginning. I don't have to convince this crowd that we're in the golden age of exoplanets, right? Over 4,000 confirmed exoplanets, mostly Kepler discoveries, but we have a huge sample of planets now that enable us to answer the big questions, right? How planets are formed, what are they made of, and how do we, our solar system, fit into this picture in the exoplanetary world, like the Earth and the solar system as an exoplanet. So the most beautiful plot that I usually show, most beautiful plot to me, of course, that I usually like to show to showcase, how diverse our own solar system is this beautiful plot from Atreya and collaborators from 2018, in which you can see, in the y-axis is this planetary to protosolar elemental abundance ratio. So basically, the ratio of what's the abundance of a given element over the protosolar abundance, what was in the proto-sun nebula, basically. And in the x-axis is different elements. You can choose your favorite element. So for instance, let's focus on carbon here. And you can see that, Jupiter is slightly enhanced in carbon, but Saturn is much more enhanced. And Uranus and Neptune, it's even more enhanced. So there's kind of a trend, right? So the first time that people look at this plot, you're just coming into exoplanets for the first time. It's kind of crazy. Like, why are the planets first different from the protosolar nebula? And second, why do they form like this weird trend? So once you start thinking about it, this trend actually starts making sense. So core accretion actually predicts that the metallicity of these planets should go as 1 over the mass of the planet. So the more massive you are, the more enhanced you should be, basically. The less massive you are, the more enhanced in metals you are. So this is exactly what you're seeing here. And actually, we are in an era in which we can actually start exploring the same trend, but with exoplanets, which is absolutely mind-blowing. But it's true. It's a true fact, as Olaf will say from Frozen. So the galaxy, actually, it's a diverse place to live in. We live in a galaxy in which there's a diverse set of systems. And they actually show this kind of trend that I was just showing with the planets in our solar system. So here, here's a very, very nice plot from the work of Luis Behuelbanes and collaborators from 2019, which actually has, all the planets in one plot, all the exoplanets and planets in the solar system in one plot. So the trends that you see here, so X is planet mass and Y is metallicity on stellar units, basically. And you can see these same trends. So, the more massive you are, the less metal enhanced you are. And this is, apparently both in exoplanets and of course in the solar system, as I just showed you before. But as you can see here, the two trends, so you have like the orangey or red tomato trend in the top for the solar system, and the cornflower blue in the exoplanets in the bottom, and they kind of not fit. And there has been, there's several questions on why they don't fit. Could it be, formation, the solar system formed differently to exoplanets, or could it be our own models? Could it be clouds, like we've been hearing in past talks about clouds and exoplanets, that they might mess up our abundance measurements? Could it be the elements that we're using? If you look at the colors, there's different elements that we're using to measure the abundance of different planets. So for exoplanets, most of them is water. For the solar system, given the colder regime in which they are, it's basically methane. So, could it be this difference? So there's, set of questions on why. This has been in my mind for a long time, and of course in the mind of all the exoplaneteers that have seen this plot once in their lifetimes. But I remember that I had like a change in direction. One time I saw a talk by Christiane Helling. I don't know if you know Christiane Helling or you have heard her talks. But Christiane Helling is, this awesome exoplaneteer. She gives amazing talks and she's very provocative. And I remember one of the phrases that she gave in one of the talks that I was hearing that, made me stand up from my chair, basically, which was there is no one abundance to extract from hot giant exoplanets. So there's like not one number. There's several numbers, and it depends on where you look in these planets. Like, to understand the comment of Christiane, I first have to go on how we actually detect these exoplanet atmospheres. But I want to plant this seed on your mind that there's not like one thing to extract, but there are several. And we typically, with transient spectroscopy, as you've been hearing in this workshop, you extract like an average one. So how do we do? We do it typically. So there's one of the techniques is transient spectroscopy, in which you basically have this planet passing in front of the star, and then you look at the transits of different wavelengths. So depending on which wavelength you look, if you look at a wavelength in which there's an atomic or a molecular feature, then the planet looks bigger. And then that's how we go on to detect and perform abundance measurements actually right now with exoplanets. Most of the abundance measurements are made with this technique. So the idea here is that you have star, you have the planet, and then you extract the transient depth as a function of wavelength, and then that's how we do it. We just extract this spectrum, and then we fit models and we extract abundance. But the point that Christiane Helling was making is beautifully explained as well on her 2020 paper on the case of HAT-P7b. But of course, this is an idea that has been around. It's just that Christiane, I think, it has been one of the first times that she has actually done like a huge 3D chemical network with clouds and throwing everything at them. And this is what you see. So here's a cut at the limb of the planet, like the same picture that I was showing you before. So this is a cut, and you see in the left panel, the gas temperature, medium panel, the nucleation rate, how good you form clouds, and in the right panel, you see the water abundance. And you see it's not homogeneous. There's no one number. So she was right, of course. There's not one number to extract for the gas temperature. There's not one number to extract from the nucleation rate. There's not one number for the water abundance. So there is no one water abundance to extract. So the question is then, if this is the case, how do we do these formation signatures in exoplanets? We first have to understand it. We have to understand first how real this is in actual data, because this is models, right? And we always want data to confirm this model. So they make, theorists in this case are making predictions, and we have to go and test them. And how impactful it is for these trends that I was showing you before. All these trends that I was showing you before were extracted with this abundance measurements. So if there's not one abundance, then how big of an effect is this on these trends? So the good news is that we know that they, of course, as being usual in the last 10 years, I think, 15 years, 20 years actually, when we first discovered exoplanets, theories are right. They predict stuff that actually happens in real life, and a beautiful picture of exactly this was depicted in this paper led by David Ehrenreich last year in Nature, with the espresso instrument, in which they found night-side condensation of iron in an ultra-hot giant exoplanet. Probably a handful of you have already read this paper in detail, but if you haven't, I'm going to give you, a small explanation of what it is, because it's such an important paper that I think it's very cool to explore what we should expect and what they saw in this article. So basically, what they did is that they observed, you already experienced this you already had an introduction to this in the lectures from Monday and Tuesday, and you also have had results being shown by you folks on the past few days. So what they did was to observe a transit of an exoplanet. In this case was 76b, and then they looked at the cross correlation map. So here's that's what in the right. So time from mid-transit in the y-axis, and rate of velocity in the x-axis, and then what you're trying to predict is how does this cross correlation map should look like in the planetary rest frame. So if you pay attention to the lecture on Monday that Nuria Casabayas-Vargas and Julia Seidel made on Monday, so if your planet is a normal planet, it has the same abundance on both sides, you should see a straight line basically at 0. This is what you should expect, like a symmetric feature around 0. So here's how it goes. So if you have some asymmetries, this is perhaps what you will be able to see. So in this case, they were looking at iron and the iron cross correlation map. And during ingress, if the hotspot, this is the green point in the bottom left figure here. The green point here is the iron abundance. And the idea that they had is that basically the point of the hottest point in the exoplanet in base side, it's slightly shifted from the substellar point. So it's like in the lower part. So that's why it's not looking directly to the substellar point. And this has been shown, in the past by several, phase curves in which you see that this hotspot shift to jets in the exoplanet, like super rotation, and all this magic that hot Jupiter shows to us in data. So where you have the hottest point, then you have basically the highest iron abundance in the gas form, because it's so hot that iron is just in the gas form. So you can detect it. So if during ingress at some point this hottest spot just aligns itself such that you see the same abundance coming from the leading and the trailing limb, so from the evening and the morning of the exoplanet, then you should see exactly what Nuria and Julia were predicting in their lecture in Monday, which is that you have a symmetric feature. But then as you go in the transit, this is the number 2 here. So as you go closer to mid-transit, then this hotspot is left behind, basically. It's like below in this picture here. So you're receiving most of the abundance of iron from the evening, actually, from this blue curve that you see in the bottom. So this means that actually the feature is blue shifted. So you see this blue shifting in the picture as well, like in the cross correlation map that I'm showing here. And then this just goes on for the rest of the transit, right? So this is what you would expect if this was the case. So the thing is that this is exactly what they observed. I'm gonna go below, back and forth with this. So this is exactly what they observed. So this is happening. It's out there. I mean, even if you don't, for some reason, I put all my hope in the express observations, but for some reason, if you have any little doubt about this, recently Aurora Castelli and Ignace Schnellen actually did a reanalyze HARPS observations, and they actually get the same thing. So this exists. Now, the problem with these cross correlation maps, of course, is that it's very hard to extract temperatures and abundances. Of many folks have been telling in the previous lectures. It's challenging to extract physical properties from these maps. So what about the abundances? What about the cloud properties? What about the temperatures in these mornings? Can you extract them? That's the big question. So the dream would be that if you imagine this toy model in which you have the morning terminator here in the right depicted in blue text, and the evening terminator in the left. So evening again is day to night, and morning is night to day. if you could, by some magic, you could extract actually the two spectra from these both sides, you can actually just try your models into this and extract the abundances and see, how different they are. This is the dream. And this dream has been on the literature for quite a while. This is not a new idea, of course. I'm not presenting you a new idea. This has been at least from my understanding, at least since 2010, which, may I remind you, was 11 years ago. So, long time to figure this out. So Jonathan Forney, actually, when he published the first 3D, or one of the first 3D models, or transit spectroscopy model, transit spectra from 3D models of Jupiters, he actually did this experiment. He tried extracting the leading and the trailing names, and he mentioned that this actually was a thing that maybe was measurable in the future. And the question is, how do you measure this? How do you go and measure these two links? How do you extract them directly from the data? So there's several ways, and I'm going to focus on one that we recently published. That again is not only our idea. This is work that we did with the awesome Catherine Jones. She's a PhD student at the University of Bern. So we teamed up together a couple of years ago, and we said, like, well, why don't we just go and fit the light curves directly with these asymmetric models? So the main idea is that you have that kind of this champignon form, right? So you have for the light curve shape. So you have one side of the planet which has a smaller effective radius, and you have the other one that's larger. And then this creates like an asymmetric light curve that you could fit to data. Again, as I was telling you before, this is again not a new idea in terms of that has been proposed before. There's a paper, at least one paper by von Paris here in 2016, in which he actually tried a similar model into this. We just expanded on that model to allow for an actual tilt and to perform these computations very, very fast, like Batman fast. So you're used to this light curve fitting. It's like extremely fast. And we put all this together in a package which is called Catwoman. Of course, if you played with light curves before, you know that the reason why we selected Catwoman is because one of the most popular light curve generators is Batman by Laura Kreitberg. And actually, Catwoman, this algorithm that does these two semicircles, it's based on Batman. It stands on the shoulders of the Batman giant in that sense. So it's figures, you can just go. And the idea, it's very simple. The idea is that basically you have light curves out there that you can actually fit with this two semicircle model, and then try to extract these features directly. So this actually allows you, if this is out there, if you could detect it, this allows you to extract transit spectra directly from the transit light curves, which is a beautiful concept on itself. So the big question is, can we detect this? And of course I'm going to go to GWST, but this has a lot of impact on what we're doing from the ground from low resolution transit spectroscopy. And it has a lot of impact on what we could do with future ELTs, which I'm going to mention in a bit. So let me focus on GWST first, James Webb Space Telescope. So what we did is that we put, this model, we said, okay, how detectable would this be if it existed? So what you're seeing here is 3 panels. The x-axis here shows the morning to evening depth difference. So how different is the depth from the morning and the evening in parts per million? So it goes all the way from 500 parts per million left, all the way down to 5 parts per million in the right. And then the y-axis, you have the light curve precision. So again, you can read this light curve precision either coming from GWST or coming from your favorite ground-based telescope. So it goes all the way from 1,000 parts per million light curve precisions, which we were seeing that people are reaching definitely with low resolution spectrographs. We just heard a talk by the Large Beasts collaboration. Access has been doing, the folks working with the BLT have been doing this kind of precisions easily from the ground. And it goes all the way down to 10 parts per million, which is kind of the GWST noise limit on the top. So the basic idea is that, of course, lower, like a higher light curve precision, like being in the top, and a larger morning to evening depth difference, like in the left, should give rise to easier to detect features, right? Because you have like a larger difference and better light curve precision. So that's the main idea of these plots. And we're putting here 3 different cases. So in the left, it's a case in which you know everything about the transit next band. You know the time of transit center, the limb darkening, the orbital parameters, like perfectly known. In the middle, you have everything but the limb darkening. So limb darkening, what it does is that it produces this curvature in transit light curve. So we were wondering, where maybe or not knowledge or poor knowledge of this curvature might impact our results. And then in the right, you have a case in which you know both the limb darkening and the time of transit center. Sorry, you don't know the limb darkening and time of transit center. So you are completely ignorant about limb darkening, but you are also completely ignorant about where the actual transit happens of your planet. So what we did is that we went and simulated light curves coming from this Catwoman model and also coming from the Batman model, the usual symmetric model. And then we just compare them against them. So what I'm going to plot here is in colors, I'm going to plot the log evidence. So basically, how much more likely is the Catwoman model, the asymmetric model with the mornings and evenings versus the Batman model, given the data. So everything. Here's the map. Here's how this map looks like. So basically, if you have precisions down to about 200 parts per million, you could detect this if you knew everything. You know the limb darkening and you knew the time of transit center. So there's a range of morning to evening depth difference that you could detect. Just to give you an idea on the range of morning to evening depth differences, some works have predicted up to 2,000 parts per million, like a very large morning to evening depth difference in some exoplanets. Some others have been predicted like 200 parts per million, 300 parts per million. So this covers all the ranges basically. The middle is when you don't know limb darkening, and you can see that limb darkening doesn't impact at all. So that's beautiful. It means that you can be ignorant about limb darkening, and that's okay. There's no diminish in returns. But then the problem is when you don't know the time of transit. If you don't know the time of transit, then it's very difficult to actually measure these light curve asymmetries in the data. The time of transit center actually tricks you into a solution, so it's very hard to detect it. So the main conclusion from this is that if you're trying to fit a single light curve, then if you don't know the time of transit center very accurately, meaning a couple of seconds, then it's very hard to detect this. However, James Webb, and of course the ground-based instruments that you folks have been speaking about in this conference, have some extra advantage. And the extra advantage is that you can look at this as a function of wavelength. And as a function of wavelength, the time of transit should be the same in all the wavelengths. So you can constrain this even better, and then you can actually overcome that degeneracy. So when you do this, so this is one case for GLGST observations. So just with a single transit, you should be able to do this. So in this case, for HAT-P41b, you should be able to extract this limb spectra as you're seeing here, and actually be able to perform retrievals on them and everything. So this is beautiful. This means that instruments like GLGST can do it, but of course, instruments like GLGST, they have their own constraints. And one of the main constraints of GLGST in this case is that it's only looking in the infrared. So there's a huge window here in the optical that you don't have with GLGST, but you do have with the ground-based telescopes. One important feature in this model in particular, if you look at it closely, in the blue region, there's a degeneracy in the at 0.5 microns. If you look at that region, so pay attention to that one. If you look to the red models, which is the possible evening hot limbs, there's like a degeneracy. You can actually go up and have this titanium oxide feature, or you can go down and have this sodium feature. So in this case, for this particular planet, for one transit observation of GLGST, you wouldn't be able to discern between them. But ground-based telescopes, in which you can do this wavelength with high precision, they could do it. So you can actually break those degeneracies, which is pretty amazing. So this is also the case from HST, of course. But of course, HST has a limited time frame. Ground-based telescopes are easier to fix. And we have upcoming ELT, extremely large telescopes upcoming from various projects that can actually enhance our capabilities right now. And here's what I want to introduce also, an alternative approach to extracting these limbs that was actually put forward by Brian McDonald, the chair of this session, which is a very nice idea in which even if you only have a transit spectrum, even if you don't have the spectrum from both of the limbs, even if you only have a transit spectrum, which is the case here in the left panel, I'm showing the transit spectrum for the same exoplanet, you can actually put some constraints if you basically just sample models from these asymmetric models, but then you add them up to form the full transit model, and then just try to predict what the transit spectrum, the overall transit spectrum should look like. So you can actually start doing this right now, and you can do it with HST even. even though you cannot extract the different limbs individually, you can anchor your solutions with the transit spectrum, with these symmetric moles that we all fit and we all love. You can actually, anchor your moles into that and then just use them to constrain the posterior distributions to say the temperatures. In this case, in the right panel, I'm showing the temperature posterior for the different limbs. Now, why I'm showing HST now and what does it have to do with ground-based transit spectroscopy, and in particular low-resolution transit spectroscopy, is that these kind of precisions we have been reaching from the ground. Like we have been reaching HST-like precision. So here's, a handful of examples. So there's, in the left panel down here, you have one of the observations from the VLT, course 2. Nikolai reached like 80 parts per million and 200 parts per million in white light for WASP-69b. So that's like HST-like precision. In the middle, some observations from our Magellan-IMAX survey. We reach again 200 to 300 parts per million in the white light easily. And Gemini GMOS, this Catherine Hudson paper from 2017 for WASP-4b, same thing, 250 parts per million. These are precisions that enable you to do this kind of work. And if you're not convinced by this beautiful white light, I'm convinced, of course, because that's why I'm showing you. But if you're not convinced by these beautiful white light curves, once you compare the actual transit spectra from the ground and HST, you reach very similar precision, if not better sometimes. So here I'm showing two examples. One from VLT Forest 2, a paper by Nikolai and Nikolov back in 2016, when they were testing, how their precision in VLT Forest 2 compared against HST. Just one observation transit spectrum, and you can see that they reach the very same precision, and they actually are able to detect the same features. Same thing here in the right with LBT mods 2. So in the northern hemisphere, this work led by Jan et al, Fei Yan in 2020 last year. Same thing. You can reach like HST precisions from the ground. So we can actually start constraining the morning and evenings from the ground right now. Like if we go to transit spectrum, we fit them in these two-limb models up to these transit spectra, and then we are able to constrain these morning and evenings. And we can go maybe even better. So it would of course be much better with better instruments. So here I'm showing, in the top plot is the same plot that I just showed you, showcasing this idea by Ryan McDonald, which you can actually feed directly the transit spectrum. And in the bottom part, I'm showing what if you try the same technique in the middle with GWST, or the technique that I just showed you about fitting directly the transit spectrum, getting the transit, the limb spectra directly from the data. So, the enhancement in the posterior distribution of the temperature, which is the rightmost panel, the last column, is much better with this future precision, of course. You have like better photometric precision, much wider wavelength range also. But it's actually the spectrophotometric precision, which is the most important, that enables you to do this kind of work. And we have, again, telescopes in the horizon ready to do this. So one of those is, of course, the EELT. So the EELT could do even better. And actually, if you go and read through the EELT, the top science, top level requirements for the EELT, for multi-object spectroscopy, which is what these low resolution works have been doing from the ground that I just showed you. So this, the characterization of exoplanetary atmospheres is in the list. It is in the list of the science requirements. My one point, and one of the points that I wanted to bring here, is that right now, there is not like a perfect instrument to do this. The closest would be one instrument that is being prepared for the EELT, which is Mosaic. So Mosaic is a multi-object spectrograph, but the problem is that it works with fibers. So the fibers are very small, like 0.7 arc seconds. So that would mean, and that's basically a killer typically for multi-object spectrograph or transit in exoplanets, because you have slit losses. So one of the things that you have to keep in mind, when one does multi-object spectroscopy, is that no photon has to be left behind. Like, I don't know if you've seen the troll. My daughter is small. I've been seeing the trolls several times. There's one phrase that they have is like, no troll left behind. So we have the same point with transit spectroscopy from the ground, which is no photon has to be left behind. And the reason is really, we don't care that the photons are left behind themselves, but what we care is that the same amount of photons are left behind throughout the night, and that's basically impossible with an atmosphere. So that's why, in multi-object spectroscopy, you usually use huge slits so you don't have this problem. You don't lose photons throughout the night. But right now with the ELT, there's not like a perfect instrument to do this from the ground. But that's not the end of the story, of course, because some of you right now hearing this, some of you PhD students, postdocs that are working on this, some of you might come with an idea to build an instrument for this. And this is the call that I wanted to make in this talk as well. I think right now the ELT is going to have huge aperture. It's going to enable like spectrophotometric precisions that are out of our minds right now. And there's this need for an instrument out there. I don't have a solution, of course. I don't have a next slide showing you this is the instrument that I propose. I'm putting this point here as a point of discussion that I think we could, revolutionize what we've been doing with transiting exoplanets from the ground with the ELTs. If we have the correct instrument, or perhaps we speak with the correct people to make some modifications to current instruments. So that's the seed that I wanted to plant with this. So again, characterization of exoplanet atmospheres, it's in the list, but right now for doing low resolution transient spectroscopy of this, there's no like a perfect instrument to do this. And I really, really think that the ELT could be a game changer on this, because there's no other instrument out there that can do stuff like what the ELT would be capable of. Okay, so I wanted to basically end my talk with the 4 points, like a summary, basically, of points based on the talk that I just gave. So the first one, again, based on Christian Helling's very important point about there's not one abundance. So the number one is that there might not be one gas abundance to extract, and we have to be way wary about this. So this is a point, and this is happening right now. So this paper that I showed you by David Ehrenreich collaborators, it's showing that this is the case. This is happening out there. So we have to include them. Number two is that the exoplanet limbs, are key windows for this 3D picture of exoplanets. So one of the things that I didn't mention is that this idea of extracting the spectra from the limbs, it's one window to 3D models that we typically have been doing, say, with phase curves, right? But phase curves are really expensive. You have to spend in some cases days around the planet in order to see the 3D structure of these exoplanets. What we're proposing here is that you can do the same thing, which is one transit, and that's it. You have some information from the 3D structure of this exoplanet, which is really, really important. Number three is that current and future data are actually enabling us to extract this information. And ground-based instruments can do this right now. So we can go on and try to push the limits of the instruments to try to extract these signatures directly. But also, as I was just mentioning before, I think the future instruments like the ELT have a huge place to play in this game. Again, can be game changers since this. And number four, which is one of the other points that I wanted to bring with this talk, or little contribution to it, is that anyone can do it. So we wrote a library to actually fit these asymmetric vectors, and you can just go use it, fit it to your lectures, and show the results to the world. So with that, I would like to finish and open the floor for discussion. Thank you.
Okay, and we've got 9 minutes, it looks like, for questions. Very nice. So please do raise your hand, anyone. Okay, I see we have a question from Vatsal. Go ahead.
Hi, Néstor. That was a very exciting talk. So you mentioned that the degeneracy between, with respect to the mid-transit, you can actually kind of mitigate that by looking at the wavelength information. And I'm wondering what could be a way to mitigate the degeneracy due to the limb darkening. So one thing I was thinking, if you have a multiple planet system, maybe you can use a transit of 2 planets with the same stellar limb darkening. But yeah, I wonder if you have any other ideas on that.
Right. Yeah, that's a good point. The first thing that I want to disclose before answering this question is that I'm sorry for the stellar models in the graph, but I just don't trust the limb darkening coefficients themselves. So my point usually is not to fit them, because we know they're slightly wrong. And for the kind of precisions that we're gonna go right now, both the precisions that we're reaching from the ground and the precisions that we're gonna reach also with digital DST, I wouldn't trust the limb darkening coefficients right off the bat. So the question then comes, into the game, in which how do we constrain this? So I think, yeah, so your idea of constraining the limb darkening with different planets, it's an idea that has been around in my mind as well. I do see one problem with this, and this is a very important problem that was put forward by a paper from 2011 by Andrew Howard. What's Andrew Howard? It was a Howard. I can't remember who it was on. I can share it later in the slide of the ESO Atmospheres, which is that when you measure limb darkening from transit light curves, even if you simulate a light curve, like, you know, go on and have your limb darkening coefficients saved, and you inject those limb darkening coefficients in your transit light curve, you simulate a transit light curve, and you try to extract those limb darkening coefficients, like even if you don't have noise, like a noiseless light curve, and you go and fit it, and you extract the limb darkening coefficients, you won't get the same limb darkening coefficients that you input it back. And I know it's kind of, it sounds kind of crazy, because that doesn't make any sense. And the point that Howard makes in his paper is that the optimizations that we do when we fit intensity profiles and when we fit light curves is totally different, right? It's not the same optimization, it's not the same function that you're optimizing. And therefore you have some biases. The problem, and this is related to your question, the problem is much more exacerbated when you have planets going at different parts of the star. So if you have, say, a planet that goes just right at the edge, right at the center, because they sample different parts of the intensity profile, you will get different limb darkening coefficients, even from the light curves themselves. So I think it hasn't been explored too much in the literature since his paper mentioning it, but I think it's a very important caveat to this idea of using different planets in a system to constrain the limb darkening. So the effective limb darkening that you want only pertains to the particular orbital solution of your planet, the planet that you're studying. So I wouldn't dare to anchor them based on this argument. And he did simulations to show this, so it's not like a crazy idea. Based on that, I wouldn't use other planets from the system to constrain the limb darkening of the planet you're interested in. Does that make sense?
Yeah, and I think with ground-based observations, additionally, you'll always have this air mass curve,
right?
So that would create additional problems. Yeah. So
yes.
Yeah, thanks.
We have a question from Sarah.
Hi, Néstor. Thanks for a great talk. So back to your very first question, you wanted to relate the answer to this fact that we don't know the exact abundances at the moment of each planet, of each exoplanet.
Yeah. So basically, the idea that we're proposing here, so there's two main points that are here in the summary. So the first point is that, right, there's no one gas abundance, so you have to be careful about this. So when making inferences about, you know, formation scenarios, CO ratios and stuff like that, that there's like not one CO ratio to extract from these planets. And we're not sure how large of an effect this has when you look at one limb and at the other. So that's the first point. The second point is that we can actually start doing this, either through the method that Ryan proposed in his paper last year, in which you have a transit spectrum and you just fit it with a 2-limb planet, and you see, okay, the range of CO ratios that I could extract is X, and if that fits your picture, great. But the other way is the way which we are proposing right now is to directly fit the transit light curves with these asymmetric modes, get the limb spectra, basically the spectrum from each of the sites, and directly extract the CDO ratios, for instance, and then compare that and see if this fits the narrative of, you know, these formation scenarios or not. Right now, we don't know because we're just starting to explore this.
Okay. Just wanted to say this could also be the difference in the nature of these exoplanets compared to solar system, because most of them are hot Jupiters, and we don't have such a creature in our solar.
That's a very good point. I think this point that you make, it's very important to realize that when we look at exoplanets, right, we're looking at a different population, like intrinsically different to what we see in the solar system. We usually argue, like the argument that we made on our proposals, of course, is, oh, you know, these exoplanets, there's a larger sample, they're easier even than some of the solar system planets. But yes, it has its challenges, and this is one of them. And this is the one that we have to have in mind. That's the main point, I think.
Yeah. Okay, thank you.
Thank you.
So I don't see any other hands raised, so I will ask a question then. Thanks for the great talk, Néstor. So thinking about what you said about how there is no one abundance.
I didn't say it. It was Christian Kelly.
Oh, sorry, there you were quoting. Well, let me introduce another thing that we have no one of. So what I'm seeing from this diagram here, and thinking back to the slide you had from David Ehrenreich's result, there also will not be one limb spectrum because of the rotation of the planet. So I want to get your take on the fact that you've assumed throughout the entire transit that there is one unique spectrum on each limb, while actually the size of the two limbs will change throughout the transit. So do you think this technique could be generalized to extract limb spectra from ingress and egress separately, so we can get 4 spectra out instead of 2? Right.
Yeah, that's a very, very good point. This point of fitting 2 semicircles is, of course, a toy model, an approximation to reality. You know, we love to make approximations to reality. But yeah, I think you're totally right. And one of the things that I've been working lately, it's on extending this thing. I'm doing like a pseudo 3D light curve fitting, in which, I mean, you do have, the problem is a geometric problem, really. So based on David Ehrenreich's picture, the problem is that it's a geometric problem in which the planet, right, is rotating. But in theory, you could extract the average from each of the sites. It's just that you would have to account for this rotation, that it's impacting your light curve. Now, my hunch, and this is, you know, I have to prove this hunch, is that for low resolution transit spectroscopy, or for measuring this in the light curves themselves, the impact would be very tiny. But again, JoJoST is going to open a huge window, and the ELT also is going to open a huge window into this that could make it important. But I don't have a straight out, like an answer straight out the bat for how impactful this geometric problem is in actual light curves until I sit down and code it up. But I think it's a really, really important point to bear in mind. In general, this is a general thing, of course. Like oral models right now are kind of toy models. We're just trying to approximate reality in some way. And this semicircle model is definitely a toy model. Like, so yes, I agree with your point, definitely.
Well, thank you very much, Néstor, and we'll move on to our next talk now. So, Suri, could you share your presentation, please?
Can you hear me okay?
Yeah, great.
Okay. This one. Looks good.
Yeah, so I'm pleased to introduce to you all for the next talk, Suri Rukdee, I hope I'm pronounced that right, sorry if I'm not, from the Max Planck Institute for Extraterrestrial Physics. And you're going to be telling us about an interesting new instrument to search for oxygen in exoplanet atmospheres. Take it away.
Hi, everyone. I'm Suri. I'm currently a scientist at the Max Planck Institute for Extraterrestrial Physics. But today I'm going to give a talk on the project I has been working on in the past 2 years at the CFA. And the instrument is called FIOS. So I'm sure that Néstor is not the only one who is excited about the upcoming giant telescope that finally we will have enough photons to do something useful. So each of these ground-based telescopes will be equipped with optical and near-infrared high-resolution spectrographs, and that would be a powerful tool for us to study the atmosphere of exoplanet. Either it's the transiting exoplanet or non-transiting one. In space, we have Ariel, which is a dedicated mission that would give you a very wide wavelength range to study exoplanet atmospheres with low resolution, and of course JWST that everyone is excited about, that would allow us to study some biosignatures. So this is the plot of the planet around M stars, the Earth-like planet one. The resolution here is 100, and it's calculated for one single transit. I would like to highlight here in the middle line that it's the signal to noise of 1 without the cloud. But there is one single piece, missing piece here in this picture, which is oxygen, right? This is one of the important biosignature, and the team knows about it. And they also try to find a new way to detect what they call the collision of oxygen molecules, which is the oxygen with other molecules. It could be nitrogen or carbon dioxide. So that's how the space-based instrument try to characterize the biosignatures. But at the end of the day, I still have to say that it's still going to be difficult in the next 10 years to study oxygen around exoplanet atmosphere. As Néstor also mentioned that none of the planned instrument is actually try to focus on these very dense features of oxygen or other dense lights. But what about ground-based observation? So in this picture, it shows the spectrum of the Earth, right? And what are we trying to do right now is try to detect this thin blue line, which is basically the oxygen band. But we try to detect it on the other world outside solar system, not taken into account that we still have very few samples of the terrestrial planet. And why do we need high resolution? I think throughout this workshop, you have heard a lot about telluric lines and also the cloud and hazes. And this plot shows a very nice explanation why we really need high resolution. It's from Kelly Hood 2020. She is going to give a talk tomorrow too, if you are interested. So within the same transit depth, with the low resolution, you basically get this black flat line or the featureless spectrum. But if you go for the high resolution observation, you have more chance to get more information into your spectral line. And then Kaltenegger 2020 also tells us that the high resolution spectra can tell us about the geological history of the molecules. Some of you may already know that oxygen was not as abundant as nowadays from the beginning. It just like bumped up 2 gigayears ago, and that's why the modern Earth in red, we have a lot of signal of oxygen right now. And if we want to implement the instrument to detect the molecular oxygen around terrestrial planet, how high do we need? So Lopez Morales 2019, she made a calculation of this high resolution that we need. So we found that the sweet spot would be around 300,000 to 500,000, as you can see in blue and green line here. But if we go beyond that, you wouldn't add up any much more information into your spectral line anymore. So searching for oxygen with ELT in this context, I would like to give an example of GCLEP, which is the first light instrument for Giant Magellan Telescope. So GCLEP has multiple observing mode, from low resolution to high resolution. And at the high resolution, it can reach 100,000 of the resolution. If we want to do the observation of transiting planet around, for example, M4, we would need around 34 transit on this giant telescope. But what about oxygen? I just told you that we need more than 100,000 of the resolution. So Benjamin, in 2018, he came up with this brilliant idea to chain the Fabry Perot together in order to create spectral chain and sample the full oxygen A band. How it works is in this figure. So you have the fiber input go into the center of the picture here. You have the reflective surfaces, and there are 8 arms, and they are almost identical. Each of them consists of a collimating lens. an ethanol and the focusing lens, and then you have fiber output. And after the fiber output, you plug it in, for example, G-clef, and that you can boost up the resolution from 100,000 to 500,000. For Fabry Perot interferometer, just in case if any of you don't know about it, it has a nickname. Sometimes we call it ethanol. So it's basically an optical cavity that you have two parallel surfaces that they are strictly parallel and highly reflective. When you feed the light into it, it bounces back and forth in between these two cavities. Part of the light reflect back and part of the light transmit to the other side. The idea of using this for observation is not super new. It was actually applied on one of the space missions called the Infrared Space Observatory. And they did do the study of the planetary atmosphere within our own solar system. And we even have the heritage from this mission in our corridor at MPE. And they did measure some of the hydrocarbon species, but unfortunately, it was decommissioned just right around the time that we found the first exoplanet. So that was unfortunate. So back to the Fabry Perot array. An advantage of using this on G-clef, on GMT, is that you will be able to decrease your observing time by 25 to 35%, which basically you can decrease or save 3 to 4 years if you observe the transiting planet. And how do we do? So we have this nice concept of the instrument. We don't know if it's going to work. So we built a prototype of FIOS. In the lab, I have the tunable laser source. I feed the source from the top of the image. It hit a prism, goes to the left of the image, to the collimating lens, to the first ethanol, bounce back and forth. Part of the light transmit to the focusing lens, and part of the light reflect back to a prism and then go into the second arm. And each arm, we have the fiber output to feed into our external spectrograph. And the external spectrograph is also a trick for implementing this instrument. It has to be high enough resolution so that you can cross disperse the Fabry Perot profile. And the external spectrograph we use for this prototype is VPAR-based. I'm not going to go into the details because it's a lot more to explain. But basically, this external spectrograph can reach around 150,000. And what do we learn from our lab demo? First we thought that this high profile Fabry Perot profiles will be able to sample the full oxygen A band. This is the simulation for 2 arms. And in our lab result, we got the desired resolution from the ethanol. And then there is this device called dualon, which is basically the multi-mirror ethanol. So you have 2 cubes basically. And it's supposed to give you a better throughput and higher resolution. And it's kind of did. So we get a nicer, clean spectral chain from the 2 dualon chain in 2 arms. And then lastly, we also thought that the fiber size that feed into the instrument would have the effect on the throughput and the resolution. And we also observe that effect. For the application, you can think of FIOS as a high resolution booster. So basically you have FIOS unit. It's a very small size, like a large pizza box, and you plug into the high resolution spectrometer. This is the detector image, right, of a high resolution spectrograph and feed with the broadband light source. So if you look closely, you will see like very thin vertical lines. And how would it look like if we plug FIOS unit in? This is how it looks like. This is the CCD image of the observation from solar spectrum using FIOS. And for the sky result, of course, we try to do oxygen event, and this looks like normal oxygen event. But if you zoom in into this doublet, you see hyperfine feature of the Fabry Perot, right? The blue one is the first arm, and the green one is the second arm. And how it looks like in the full picture of oxygen event. Can you recognize the doublet of the oxygen? So instead of very thin feature, you get a fatter line, and it means Fabry Perot array help you to sample your data better. And the ringing are basically the resolution of 600,000 of the Fabry Perot. And I think that brings me to the conclusion of my talk. So we have a new way that we can boost the spectral resolution to 600,000, and we try to detect the molecular oxygen around terrestrial planet. And one idea that I also would like to put a seed in is that FIOS-like instruments should be on all the ELTs. One idea is to plug it in high-res, which would give an opportunity to implement FIOS in oxygen and methane channel, and that would give a chance to detect biotic oxygen, and that would be extremely exciting. So if you are interested to talk about this more, you can write to me, otherwise I would take the question. Thank you.
Thank you very much. So do we have any questions? I don't see any immediately, so I'll go ahead and ask one of my own. So I'm really excited by these like incredibly high resolutions that you have here. And one application that came to mind that is a consideration we're often hiding in the back of our models is about the line shape of resolved spectral lines. Usually for our exoplanet models, we just assume we've got void profiles everywhere unless we're dealing with like the resonance lines of sodium and potassium. So could you use like the very high resolutions that you have here to like empirically measure deviations from void profiles so that we could, I don't know, get some kind of improved pressure broadening prescriptions that could make our models better?
So first of all, a modeler might have to revisit the model for this high resolution. But the profile, if I model the instrument, and also what I did was to use the Fabry Perot profile. And like, we can go back here. So in this plot, you can see I basically put the how Fabry Perot would behave in the system, and then after the first arm, you have the output light, and then you feed that into the second arm, and that you can model them together. And then for the other arms, I think we just continue doing that and just put overlay on top of the high resolution spectrograph. And the shape would be similar to this, but I did have to do some convolution so that it fits, because it's, of course, when you have the real life profile, it's not perfect. So you have to do some convolution for that too.
Thank you. I see we have a question from Elia.
Hi, thank you for the talk. I was wondering how efficient is the ethalon or the duolon, because my worry is that obviously the more you disperse the light, the more you reduce your signal to noise per pixel. And we are, obviously, to detect exoplanetary atmospheres, we are performing time domain spectroscopy, so we are kind of limited by our exposure times. So have you thought about any current targets that we have that would allow to even try and observe this in limited exposure times that we currently have?
Limited exposure time, that's very difficult because, yeah, as we know, if you go higher resolution, you have to, you have to exchange with your exposure time, right? But the point is, using this, you can reach the significance of detection easier.
But you remember that the signals that we are trying to measure, they're not stationary, they're moving. So if you observe it for an hour, you are completely going to basically smear out any individual planetary absorption line, because of course the planetary radial velocity is changing. So I'm just wondering in terms of in a practical sense how we would do it.
Yeah, that's why I also try to convince that it should be on all the telescopes, so you can switch between the observatory, and that you can.
It would be interesting to do the calculations for an ELT, let's say, and see for the brightest targets that we have what sort of signal to noise we would get. But no, I mean, obviously this is, I mean, we do need this kind of resolution, obviously, to resolve O2. I think there's been papers by Ignace Snellen also talking about this. So yeah, I'm just thinking in terms of in a practical sense. Thank you. Thank you for the talk.
Okay, I think we will go on to our final talk of the day then. So, Kazumasa, could you share your slides, please?
Sure. Can you see my screen?
We can indeed. We can indeed. So, gives me a great pleasure to introduce our last speaker of the day, Kazumasa Ohno, who's going to be telling us about aerosols in escaping atmospheres and the implications for transmission spectra and the origin of superpuffs. By all means, go ahead.
Yeah, thank you for the introduction. My name is Kazumasa Ohno. I'm currently a postdoc working at University of California, Santa Cruz. And I'm mainly working on the microphysical modeling of aerosol formation, such as condensation clouds and chemical hazes in exoplanetary atmospheres, as well as solar system objects. And today, I'd like to talk about how the aerosols grow and move in escaping atmospheres of exoplanets. Especially, I will focus on the low mass, low density planets, so-called superpuffs. Low mass planets are common in this galaxy, and several low mass planets are found to have the radii that are comparable to the radii of gas giants. And because of their very low bulk density, they are called superpuffs. Interstructure model suggested that their large radii can be explained by the presence of very massive atmospheres with about 10 to 38% of total planetary mass. Because such massive atmospheres on the low mass planets are very unique properties, the superpuffs are currently very attractive targets to study atmospheric properties as well as their formation and evolution history. Superpuffs are interesting because there are several remaining puzzles about their atmospheres. For example, it is not easy to explain why such low mass planets like superpuffs have such massive atmospheres. According to planet formation theory, it is not easy to accrete such massive atmospheres on low mass planetary core. Even if such a low mass planetary core can get a massive atmosphere, they tend to grow into gas giants because the atmospheric mass estimated for a current superpuff is close to the threshold value to trigger the runaway gas accretions. So even if the superpuff succeeded in getting a proper amount of massive atmosphere somehow, so it is still not easy to sustain such atmospheres until today, because such low mass planets are very vulnerable to atmospheric escape because of weak gravitational binding. Another pathway is coming from the recently observed transmission spectra for several superpuffs. It was initially expected that the superpuffs likely produce very large spectral features because they have the very large atmospheric scale height due to low surface gravity. But in reality, the observed spectra are mostly featureless, and their spectra cannot be explained by the cloud-free atmospheres. So the recent studies discussed that the low-density nature of superparks may be caused by other reasons. So, for example, some papers discussed that the very low density of exoplanets might imply the presence of circumplanetary ring. So another promising idea is that, so because the atmosphere is likely very cloudy or hazy, as suggested by transmission spectra, such a very cloudy or hazy atmosphere might enlarge the transit radius significantly. So I'm now focusing on the second idea. So this idea was originally proposed by the Wang and Dai 2019. They suggested that because the low-mass planets likely experience the intense atmospheric escape that can drag atmospheric dust to upper atmospheres. Such atmospheric dust or aerosols in upper atmosphere can enhance the transit depth significantly. So they performed the hydrodynamic simulations, including atmospheric dust as a passive tracer, and showed that such dusty outflow can enhance the transit radius by a factor of 3. So it is very interesting results, but they assume that they adopted several simplifications. For example, they assume the constant particle size and the constant aerosol abundance. It is not necessarily true. And also there are several remaining questions. For example, so we don't know what kind of the aerosols is responsible for this process, and how does such a dusty outflow affects the transmission spectra. So we use a microphysical models to further study this dusty outflow scenario in this study. So we simulate the evolutions of particle size we simulate the growth of aerosol particles in escaping atmospheres using microphysical models that was originally used for modeling haze formation on Triton, the largest moon of Neptune. In short, the model is computing the evolutions of particle size distributions at each radial distance by including some transport mechanism, some transport process, as well as the microphysical process to driving the particle growth. In this study, so we include this vertical transport by escaping outflow and gravitational settling of aerosol particles, as well as the collisional growth. And for the sake of simplicity, so we assume the spherical particles for most simulations, and we neglect the condensation growth of aerosol particles by saturated vapors. Also, it has been currently unclear what kind of aerosols is responsible for dusty outflow scenario. So we parameterize the aerosol production using log normal distributions. And we adopted the isothermal Parker window model for the sake of simplicity. And this figure shows some examples of the computed size distributions. The color contour is the mass density in each mass grid. And the left and right panel shows the distributions for the aerosols formed at 10 to the minus 6 bars and 10 to the minus 2 bars, respectively. The distributions are considerably different between these two cases. For example, so when the aerosols is formed at very upper atmospheres, they are relatively easily dragged to upper atmospheres by escaping outflow if the atmospheric escape is strong enough. On the other hand, if the aerosol is formed at a deep atmosphere, they tend to go down to deep atmosphere because they experience very efficient particle growth, and only a small portion of aerosol particles can be dragged to the upper atmosphere by escaping outflow. So this figure shows the aerosol abundance in the escaping outflow, which is measured at 10 to the minus 9 bar. And the horizontal axis is the normalized production rate. And if we completely neglect the gravitational settling of aerosol particles, the aerosol abundance becomes the value of the horizontal axis. And we can see that the aerosol abundance in the outflow is highly depending on where the aerosol is formed. For example, if the aerosol is formed at 10 to the minus 4 bar, the aerosol abundance is about 3 orders of magnitude lower than that expected for aerosols formed in 10 to the minus 6 bar. So the formation altitude is very important. So this figure shows that transit radii, including the dusty outflow, normalized by the radii without the dusty outflow. And we can see that if the dust is if aerosol is formed at deep atmospheres, such as 10 to the minus 2 bar, the dusty outflow hardly affects the transit radius. And in order to achieve the radius enhancement by a factor of 3 or 2, as suggested by previous studies, so aerosols must be formed at upper atmospheres, such as 10 to the minus 6 bar. So this gives us some constraints on what kind of aerosols can be responsible for this dusty outflow scenario. So condensation clouds are unlikely responsible for this process because they are typically formed at relatively deep atmospheres. And high altitude aerosols such as photochemical hazes and meteoric dust are more promising candidates. And especially for the temperature range, for the typical temperature of the super pulse, which is below the 1000 Kelvin, the recent studies suggested that the photochemical haze may be universally present in such cool exoplanetary atmospheres. So we suggest that the photochemical haze is likely the most promising candidates that can act as a radius enhancement factor. And this figure shows the transmission spectra, including the hazy outflow. In general, the transmission spectrum becomes more featureless as the aerosols is formed at more upper atmospheres. But if the aerosol is formed at the extremely upper atmosphere, the spectra becomes rather feature-rich in the infrared wavelengths, and also spectrum shows a super really steep spectral slope in the visible wavelengths. Such a feature-rich spectra can be merely due to that the hazy outflow becomes optically thin in that wavelengths. And this super Rayleigh slope can be explained by the steep vertical gradient in the atmospheric opacity. So if we see the vertical distributions of aerosol mass mixing ratio, so we can see that if the aerosol is formed at extremely high altitudes, so almost all aerosols are transported to upper atmospheres, and the atmosphere below the aerosol production region becomes clear. And this structure creates a steep vertical gradient in aerosol opacity from bottom to top. And my previous paper shows that such vertical opacity gradient can steepen the spectral slope. And this process can explain the steep spectral slope in this figure. So our synthetic transmission spectra can explain the basic properties of the transmission spectra observed for real superpuff planets. For example, if we assume reasonable parameters of atmospheric mass loss timescale and the aerosol production regions relevant to photochemical haze, so we were able to explain the observed radius of Kepler 51b as well as its feature spectra in near infrared wavelengths. So we tested several different optical properties of aerosol particles to account for the uncertainties about the aerosol compositions, but the general shape of the transmission spectrum is the same. But we found that for some specific aerosol compositions, the spectrum shows the absorption features of aerosol itself because the atmospheric escape can drag only small particles. So if it is that such an absorption feature can tell us about the information on the aerosol compositions. The more general trend is that the transit radius of superpuffs should drastically decrease with increasing wavelengths because the such a dusty outflow consists of small particles. And such a decreasing trend can be tested by the upcoming observation by GWST and maybe also tested by the ground-based telescope. And we also suggest that such transmission spectrum is useful to test different scenarios on the origin of superpuffs. So we computed this transmission spectrum of planets surrounded by circumplanetary ring, and we found that the transit radius of ringed planets does not decrease with increasing wavelengths, in contrast to the planets with dusty outflow. And this is basically because the circumplanetary ring likely consists of huge particles according to previous studies. So we can use a transmission spectrum to test the different scenarios on the origin of the low density nature of superpuffs. So lastly, I'm trying to discuss why are superpuffs uncommon. So the recent studies discussed that the photochemical haze are likely ubiquitous in a cool exoplanetary atmosphere. And then someone might think that why not all hazy planets become superpuffs? So to answer this question, so we computed the ratio of the 10 to the minus 8 bar to 10 to the minus 2 bar transit radius, which is computed by interior structure models. So this value roughly estimates how much the atmospheric aerosol can enhance the transit radius if the aerosol can make the upper atmosphere opaque. And we can see that basically the radius enhancement is efficient only for the very narrow range of planetary mass. And for the range of high planetary mass, basically this radius enhancement is almost negligible, even if we artificially put the opaque pressure level at 10 to the minus 8 bars. So this radius enhancement can be significant for low mass range, but for such phase space, the atmospheric escape is too strong and it is unable to sustain such atmospheres. The reason is actually a bit simple. So because the degree of radius enhancement is scaled by the ratio of the atmospheric scale height to the planetary radius. So in order to achieve the significant radius enhancement, the pressure scale height must be pretty large. But it has been shown that such large atmospheric scale height causes an intense atmospheric escape that tends to cause a total atmospheric loss. So if we plot the superpuff candidates compiled by Shashan et al. 2020 in this diagram, we can indeed see that the majority of superpuff candidates are located around this narrow mass range. So we suggest that the photochemical haze can influence the transit radius only when the planets verge on total atmospheric loss. So this might explain why superpuffs are common despite the suggested universality of photochemical haze. That's it. Thank you for attention.
Thank you very much. So, do we have any questions? Please raise your hands. I'm not seeing any questions at the moment, so I will go ahead and ask one then. So could you go back to the slide for a moment where you had the comparison between the ring system and aerosols? I thought that was a really, really nice diagram in particular.
Okay, sure. This one?
This one, yes. So, I think one more slide there. On
my computer is a bit heavy.
So my question was, I was curious into like how you calculated the transmission spectrum for the ring system and what kind of additional physics and complexity went into that doesn't normally have to go into transmission computations. Thanks.
Okay, so basically we assume there's some artificial gray opacity layer between the the loss radius to the ring inner rim. So basically the ring outer edge is expected to be around the loss radius of planets, so we can calculate that from the planetary planet density. And I also assume that the inner edge of the circumplanetary ring is about half of the outer edge. So I put the gray opacity layer in that region, and I just compute the transmission spectra by including such a gray opacity layer to mimic the circumplanetary ring.
Thank you. Do we have any other questions? Well, if not, then I think we will wrap up today's talks. We do have one final quick announcement. So to all the speakers, we'd like to be able to put up PDFs of all of the various talks, as long as they're not embargoed. So I'm just going to share into the Zoom chat and also on Slack an email address, where if you could kindly